Okay, good afternoon, everyone. This is the third session of the FairHeat 6th anniversary extravaganza. We have had this morning, we had a session on transitioning to low carbon heat and how we do that. The second was a technical session where we went through a number of a series of different presentations. This third session, we're looking at how we decarbonize heat networks specifically. Exciting session. One thing I just want to note, we are recording this session, and so we will also be publishing the recordings following this. Agenda today, we're going through 3 different sessions. So the first is around optimizing existing heat networks. The second session is about decarbonizing existing heat networks. So first 2 on the legacy side. And then the third is really looking at new build heat networks and how do we integrate heat pumps into those new build heat networks, because that's obviously a topic which is important in the industry at the moment. Then we're going to wrap up with a panel session with questions and answers. If you do have questions through, there's a Q&A, please just log your questions and we'll come back to those at the end. I'm going to hand over for the rest of the session with Tom Naughton. He's going to be hosting from this part on, and will be moderating the panel session at the end. So we're on to the first session, and I'd like to make an introduction. Tom Naughton, Associate at FairHeat, Lina Aglen, who's a lead engineer at FairHeat, and then Joel Hamilton, Heat Network Specialist from BEIS. Thank you.
Thank you, Gareth. Yep. Afternoon, everyone. As Gareth said, so this first presentation will be about how to optimize heat networks, and particularly with respect to a project that we carried out in partnership with BEIS, looking at optimizing legacy heat networks. So at this stage, I'll actually pass you over to Joel Hamilton, Dr. Joel Hamilton, Heat Network Specialist at BEIS, and he'll just start the presentation by introducing what the HNOO, the Heat Network Optimisation Opportunities project was about. Thank you, Joel.
Hi everybody. Thank you, Tom. If it's possible, go to the next slide, please. So why did we do this? Also, just a bit about me. So as was said, I'm in the Heat Networks team in BEIS and Department of Business, Energy and Industrial Strategy. So at the moment, we know that there's about 500,000 customers spread across 14,000 heat networks, of which about 2,000 of them are sort of district heating networks, and the rest of them would be communal. And the difference between those is communal networks are where you tend to have multiple customers in one building, like a block of flats, and district is where it's spread between multiple buildings. Heat networks currently provide 2% of the UK's heat demand, but they are integral to all of the heat decarbonisation pathways that we're currently assessing. And even in 2015, the Committee on Climate Change was estimating that around 18% of heat demand would have to be delivered by heat networks. As I said, they play a really important role in meeting our carbon targets, not least because they allow you to access quite difficult to get to low carbon heat sources. So it's quite difficult to get waste heat from the source to someone who needs it without a network of pipes moving them. They allow you to also have sort of economies of scale and a bit more control over the demand and supply as well. So they're quite an integral and useful part of this pathway to net zero. However, can we do all of this if the heat network's reputation is tarnished by performance issues or unsatisfied customers? And so this is where the Heat Network Optimisation Opportunities project came along. So if you go to the next slide, please. So what's government's role in supporting existing heat networks? We had done in the past a number of sort of discrete studies into some of the challenges with existing networks, but there's been it's been a very difficult process within government to see how we can support existing networks effectively. And what is it that is really needed? So the HNOO program really gave us an opportunity to learn and understand. And really is to learn and understand what the optimization opportunities are. So this isn't only networks that are really struggling, but just ones that could do a bit better. Why do these opportunities exist? What can be done about them? And why is it not already happening? And what is the decarbonisation pathway for existing networks? So if you go to the next slide, please. So what did we do? We funded 21 separate studies, 21 separate sites, over 3 organisations, of which FairHeat was one of, each with a unique approach to looking at optimisation opportunities. Then we wanted to present the findings in a form of a sort of technical business case with the project sponsors, and that's typically the project sponsors in this context is usually the site owners or operators. Then we get to discuss with them what's going to happen next. And also what was really important for us in government was to create a dialogue between the project sponsor, the technical consultants like FairHeat, and ourselves to understand what the issues are and what we can do to help each other to try and overcome them. And then also what's really important is that we can take all these lessons and use them to influence other decisions within government in terms of heat decarbonisation. So next slide, please. I think I'm handing back.
That's great. Thanks, Joel. Okay, so on to the project from our perspective, from FairHeat's perspective. The requirements we had were that it would have to be existing residential heat network projects, both communal and district heating. They obviously had to have suboptimal performance, so there was opportunities to improve that performance. Another key requirement was that there'd be a lot of data available because there needed to be objective analysis done, and it would really help build a business case that was based on hard numbers. So the outputs of the project for each of the projects we worked on would be robust business case for a series of potential packages of works. And those packages of works had to be cost effective, and they had to demonstrate that there'd actually be a quantifiable improvement in the performance of the heat network. So we approached a lot of organisations that we work with currently and asked them if they had any heat networks that fitted the bill. The reasons came back from clients about why they would like to include their heat networks were very high electricity bills, that some of the networks had equipment that was sort of 40 years old and the whole system was reaching the end of its technical life. There was a lot of maintenance issues with main equipment, boilers and HIUS in people's dwellings, lots of resident complaints and customer sort of dissatisfaction, and that they believe there'd be potential to improve the performance of those systems. Okay, so in total on this project, so Joel mentioned that there were 21 projects in total that we worked on. That BEIS worked on this project. Of those 21, we worked on 10 of them. Of those 10, we were aiming for, which again was a request from BEIS, from the project, to be as varied as possible because we wanted to capture as much of the market. So we looked at developments from being built sort of 50 years ago up to developments that were literally handed over the year before. Again, on scale, 75 units, typical communal heating system in London, those kind of scales, all the way up to, we looked at 950 dwelling units, which were big district heating systems. And in total, across those 10 projects, there was 3,232 dwellings that we looked at as part of the overall project. Of those 10, 9 were district heating networks. As Joel mentioned earlier, that meant that there was more than one building connected to that heat network. In many cases, it was only sort of 2 or 3 buildings. These weren't big district heating systems, and one of them was a communal network. a broad range of heat network operators. So we wanted to make sure we covered social housing associations, local authorities, but also the private market, so private developers and ESCOs. And the main heat production, these are legacy systems, unsurprisingly, around gas boilers were dominant. There was one air source heat pump project and one that was actually fed off an existing district heating system. So it had a plate heat exchanger. The project methodology is we did an audit of the sites. That's data going to site, going to dwellings, going to the energy centre. It's very important to be sort of hands-on, actually physically see how the networks are working. Then there was a data gathering exercise where we collected operational data from the Guru pinpoint system and from any BMS systems they had on site. Reviewed the assets, the equipment installed, reviewed maintenance logs. We also interviewed or spoke with O&M contractors to understand what the legacy issues were on that site. And then through that process, we could identify optimization opportunity by building an actual model of the heat network, and then coming up with a series of interventions and then testing those interventions on the heat network so that we could actually objectively see what impact that would have on heat, for example, heat losses on the system or the performance of the heat generating equipment. And then we provide a full costing analysis of the capital cost to carry out the works. And then all of that information then went into a financial modelling and a preparation of a business case back to the sponsor. That business case would include typically 3 work packages, which range from easy wins to very work-intensive improvements. So easy wins, things that could be implemented quickly and with improvement, and then maybe more work-intensive programs that will typically include things like replacing capital equipment. And then on each of those work packages, we do a financial analysis, which we try to incorporate all of costs as possible. So not just things like capital costs of equipment, but also the labour costs to do it, the project management, the internal costs of the organisation to actually manage that project, and then the ongoing management and maintenance costs of that. And through that, we produced net present value and IRR results for the different work packages, simple payback, and a sensitivity analysis of the project. I'm just going to pass over to my colleague Lina, who headed up a lot of the program for FairHeat on this side, and she's going to run through some very high level results.
So,
okay,
can everyone hear me? Hello?
Yes, I can hear you.
Perfect. So, as mentioned by Tom previously, the suggested works that were investigated as part of this program of works were bundled into different work packages, where work package 1 would generally consist of the more lighter intervention works, and work package 3 would generally consist of the most comprehensive works. And across the program of projects, the simple payback for improvement investments were on average less than 6 years. And for work packages 1, the simple payback was on average less than 3 years. Aside from being associated with quite attractive business cases, carrying out performance improvement works also have the potential of significantly lowering costs back to residents. And we can see that already with work packages 1, a significant annual cost saving is enabled for. And if we split that cost saving to be per dwelling on the network, we can see that there's a significant potential for cost savings to be carried over into lowering the annual cost for residents and end users. As more comprehensive works are carried out, the annual potential cost saving per dwelling increases. And this plot here below shows all work packages proposed for the 10 projects under FairHeat's HNOO scope, mapping the CapEx requirement on the x-axis against the potential annual cost reduction on the y-axis. And aside from a couple of particular outliers, we can see that there's a very clear trend in that the more CapEx you invest into your performance improvement, the more potential there is for cost reductions. Now, some interventions do come with quite a high associated CapEx investment, but there are also a large number of interventions that have a relatively low CapEx associated, but still contribute to a significant potential cost saving, as we can see from this sort of cluster of items collected at the bottom left corner of the graph. And to look at some of the more specific interventions that are low cost but do contribute with easy gains, we can see that in many cases there were oversized equipment, where equipment such as pipework and radiators were found to be oversized, which means essentially that system temperatures can be dropped without needing for any more invasive works across the network. And this is an item that will be further developed on in detail by my colleague James later on in this session. A second very common but very simple work to carry out to improve network performance is to close network bypasses. And to illustrate this, I've featured this image to the right, where we can see a top of riser bypass that's open between the flow and the return on the network, where closing this bypass is merely a case of pulling these two levers and ensuring that they're being kept closed. Two other very common work items that were suggested that are relatively cheap and very easy to enable for is to enable controls and carry out commissioning of equipment. So if you are a network operator and you've been sitting here thinking, what's wrong with my network? Well, this slide is for you. And based on the 10 schemes that we investigated as part of the HNOO program, we have a pretty good gauge of issues that are commonly recurring across the different networks that we took a look at. We could see that 9 out of 10 networks had an uncontrolled pump operation, which results in increased electricity consumption and cost. 8 out of 10 networks had an uncontrolled plant operation, which results in decreased generation efficiency. We could see 6 out of 10 networks had open network bypasses, which drives return temperatures, heat losses, and pump electricity consumption. We could see that 8 out of 10 had large portions of uninsulated pipework on the network, which drives heat loss. And all 10 networks investigated had instances of poorly performing HIUs. And if you remember from the last slide, these are all items which can be rectified at a relatively low cost. When it comes to specifically around poorly performing HIUs, it's possible to identify, if it is possible to identify particularly poorly performing units, then HIU recommissioning can be carried out to a very low cost, where this is an excerpt from Guru Pinpoint, which can be used for performance analysis and for identifying poorly performing units in order to target these specifically for maintenance. As an example of the impact that this can have on the network performance, on one of the investigated networks, we identified one single bypassing HIU, which contributed to more than 60% of the total network flow requirement, which resulted in a significant increase in the network return temperature and drove heat loss and electricity requirements for the site. So by targeting maintenance into particularly poorly performing dwellings, that can therefore have a significant effect on the overall network performance to a relatively low cost with relatively little intervention. If you're wondering why I'm going quiet, it's because there's a slight delay in me swapping slides over. There we go. So most of the interventions that we investigated were associated with positive business cases, and the analysis that we carried out per default and the results that I presented earlier for example, simple payback, they did not consider what's called the cost of carbon, which is a theoretical figure that's aimed to address the cost of the negative environmental and social impacts of carbon emissions. And using figures for cost of carbon based on the Green Book by BEIS, we were able to include the cost of carbon in alternative business cases for each of the projects and work packages in order to take into consideration and place value in the potential decarbonisation, which would be enabled by the performance improvements. And we can see that if we take the cost of carbon into consideration, all the business cases do improve significantly. where, for example, for old work packages 1, the average simple payback is reduced from on average 2.7 years to 1.9 years.
Excellent, thank you, Lina. I think that's just going to hand back over to Joel. So that was the conclusion, the results from our perspective. I think from BEIS's perspective, Joel, what were your conclusions and what were your kind of next steps?
So, I mean, that was really helpful. Thank you for going through all the detail. And as a fellow engineer, I found this whole project really, really interesting. And I was really grateful that I wasn't the one running around in the plant rooms as well. So I got the benefits without getting covered in cobwebs. So for BEIS, there's several elements of the conclusion. So one is the opportunities. So there's the ones already mentioned. These energy and emissions and cost savings, and they're really a benefit to everyone. There's the direct benefits of saving money for either the operator or the end user, the heat customer. There's also an air quality benefit as well as a carbon benefit. As I'm sure we're aware, a large number of these heat networks can be in quite densely populated areas, which would have other air quality issues as well. So it's good to know that there are things that could be done fairly easily that can alleviate some of this environmental and health issues. There were lots of common themes, or you could call them common problems or common solutions. It depends on which way you want to look at this, glass full or half full or half empty. As highlighted by Lina's slide, the number of the sites that had fundamentally fairly straightforward problems that could be solved was really interesting. And what's really good about it, although it's a shame they exist, is that we could then utilize these common problems and solutions to make a really big difference across the whole sector. Because through a bit of guidance and a bit of support, these things can hopefully be significantly reduced. And I think another part to this as well is that all the projects that we've looked at now, if they do choose to take on the findings and the recommendations from the reports, they have a path to net zero, or at least a path to low carbon operation, and doing it what seems to be the sort of the sensible way round, if I'm allowed to use such a term, where you look at what you've got first, you optimize that, you reduce the operating temperatures and requirements, and then you're ready for any other plant that you want to put in there, rather than just going straight for some low carbon plant without actually addressing some of the fundamental system based issues. Could I get the next slide, please? So there were other, within the conclusion, there were other challenges. It goes without saying that COVID caused some pretty significant challenges all round. This project started well before the first lockdown, and there was a number of points where we had to review how we were going to move this forward. And I'm really grateful for the team at FairHeat because they did a fantastic job. They didn't let the inability to go and do all of the investigations they wanted to do get in the way of being able to deliver really high quality outputs that can make a significant difference to the sector and to the sites that they looked at. There were technical challenges, but as I put on here, most of the technical challenges I think are solvable. Really, the reports show that, and I'm sure at some of the other FairHeat sessions they talk you through some of the quite solvable technical problems. The ones that sort of really I think became quite interesting in terms of stumbling block, probably for more people, for most people, as an engineer I quite like the technical problems, but were these institutional ones. So there's challenges on how the structure of the organization can prevent the receipt of benefits. And what I mean by that is that if you're not allowed to hold on to a financial benefit from doing something, it's very difficult for you to make a case to invest. Or even if you are allowed to take benefit, or if your organization can take benefit from some savings, if your organization's set up in a way where you've got a maintenance budget on one side of the organization and a capital works budget on the other, and another site that deals with the ongoing just operating costs, and they don't talk to each other, you then have a very difficult challenge of saying, well, this project can pay back in 5 years. Can I have some money, please? And that's something that is a really interesting challenge, and it's different for each organization that we worked with. Some of the commercial returns are not suitable for investment, and so maybe alternative models of looking at why you're going to invest if it's beyond the realms of commercial returns, and how to get around that. There was also some sort of lack of ownership of issues. There was one site in particular where there was probably about 6 people who joined the call, but none of them were actually responsible for looking after whether the site was running properly. And that was quite an interesting thing. How do you make sure that someone can take ownership and really try to make these sites operate better and have as minimal impact on the planet? And a key one that I think you see across the board, not only in the heat network sector, is a lack of monitoring resource. It's all well and good going and setting things up and optimizing it, but if you've not got someone checking it regularly to make sure that things are actually still performing properly, you very quickly slip into that poorer performance situation, which kind of led to these optimization opportunities existing. And there's also some personal things, which was, and this is more like just like sort of people traits, really. What their priorities are, motivation and determination. In some organizations, there can be 1 or 2 key people who just really drive this message home, and I think that's not to be underestimated. Having people who really want to take these challenges by the reins. So that was that would be the challenges. If we go to the next slide, please. So what's next? So positive stuff, because this was a really interesting piece of work that we did. We got some really good findings from it. So there's a watch this space on a program called the Heat Network Efficiency Scheme, which is kind of the follow on from HNOO, from Heat Network Optimisation Opportunities, and we're developing a project to support the part funding of operational improvements in these networks. So it's finding a way to overcome some of the commercial challenges around the recommendations that were put forward by the reports, like the ones done by FairHeat and others that are in the market. And we're going to announce some more details on that later this year, but as seen from the data here, that can significantly reduce emissions and costs for people. And then a really big part as well is just feeding back these findings into future regulation and funding programs. So you've got the Heat Network Market Framework, I'm sure many of you are aware of. There's the Green Heat Network Fund, which is a £270 million successor to HNIP that can be used for low carbon plant upgrades. And just as a snippet, I mean, I was asked a question which said, is there an issue with requiring there's reasonably low flow temperature requirements? I think it was sub 60. And actually the findings from this work allowed me to answer that with a reasonable confidence, saying most of the projects that we looked at, there wasn't much, if any, problems in actually reducing the flow temperatures to 60 degrees. So that was a really interesting finding that straight away from this project got to feed back into some other areas that's happening within government. So yeah, I just want to say thanks to the guys at FairHeat for doing such a great job on this. And I think I'm handing over to someone else now.
Excellent. Thank you, Joel. It's really good to hear that the outputs are feeding back into policy and regulations as well. Actually, I just wanted, if you just pop to the next slide, I wanted to say as well, there's a huge amount that went on in HNOO, as you can imagine, with the 10 projects, different types of projects, lots of different, whilst there were common themes, there are also lots of different sort of issues that we discovered. We're going to have we've got 20 minutes here, 25 minutes. We're going to have an opportunity to go far more in depth into this in 2-3 weeks' time. So we're having a morning, a coffee webinar, as it was, on Wednesday, the 17th of February. And again, that'll be attended by BEIS, and we can go into a lot more detail about what we found, what recommendations we have, and the challenges. But thank you Thank you both. You both will stay on for the panel discussion, but thank you both for your input in this. Excellent. And another comment you made, Joel, which segues perfectly into the next presentation, is about getting, so we've looked at how to optimize heat networks, existing systems, and now still on the subject of existing systems, how are we going to make them compatible to integrate them with low carbon technologies? As we saw, most heat networks at the moment are run off gas and fossil fuels. How are we going to transition that? And a lot of that is around temperatures and optimizing the performance of existing systems. So moving on to the next presentation. So this is about how we kind of decarbonize existing systems. And I'll be presenting again on this one, but I'm joined with my colleague, James Gallimore, who's a senior engineer, who will take us through a specific case study called Wharf, which is a Notting Hill Genesis project. And I'm delighted that Laura Shallard, the head of energy provision for Notting Hill Genesis, can also join us. She'll provide some comment on overview of the Wharf project, but also talk about some of the challenges from a housing association perspective towards decarbonising their existing stock. Okay, so anyone who's been to the previous two sessions will be aware of a lot of these numbers, so I won't dwell on them too much, but about 2% of UK heat demand is currently on heat networks, and those heat networks predominantly use gas boilers and gas CHP, so fossil fuel technologies, which is obviously something we're going to have to transition away from over the next 10, 20 years. And there's an aspiration that by 2050, 20% of UK heat will be delivered by heat networks. And of course, by 2050, that will mean that those heat networks will have to effectively be net zero. So what that means from a generation perspective is I'm going to, and apologies for hydrogen fans, but I'm going to completely ignore hydrogen here. That probably means, from my perspective, that there's going to be a significant electrification of heat, and that'll be electrification of heat through heat networks as well as through electrification of heat for individual houses. And why is that? Well, as you can see, this graph shows the carbon intensity of UK electricity since 1970. Up to about just pre-2020, and then there's a series of projections moving on from 2020. But what it shows is there's been a drastic reduction, particularly post-2010. So between mid-90s to 2010, there wasn't much movement, and then in the last 10 years, there's been a significant reduction in the carbon intensity of the electricity grid. And what that means for a heat generation perspective is that heat pumps, so this graph shows the carbon intensity of the heat delivered to a resident with some assumptions. So whether it's, so the blue line is gas boiler, so you've got natural gas going into the boiler, 85% efficient, which is a good sort of rule of thumb. And then you have 15% losses on the heat network. That effectively means you're delivering a carbon intensity of heat of about 0.3 kilograms. Assuming, there's a question about there could potentially be some decarbonisation of the gas grid, but it's not likely to be significant towards net zero. So assuming that stays fairly stable across from now to 2050, and then in comparison, the orange line shows the carbon intensity of heat delivered to residents on a heat network via a heat pump. So this particular example just assumed an air source heat pump running at a seasonal COP of 2.5, which is actually very conservative, with the same heat network losses. And you can see already at 2020, the carbon emissions from an air source heat pump compared to a gas boiler is significant, and that's only going to drop with the getting close down to net zero by 2050. However, we can't just fit heat pumps into legacy buildings. Legacy buildings tend to have higher operating temperatures, so whether that's they have hot water cylinders or radiators, the fabric efficiency isn't so good. so they need to operate at higher temperatures. But unfortunately, how heat pumps are, the efficiency of a heat pump is governed by the temperature that you produce heat out of that heat pump. And you can see in this graph, so we've just taken a very common heat pump on the market, looking at the efficiency, so the COP on the left axis is effectively the efficiency of the operating. So if you have a COP of 3, you put in 1 unit of electricity, you get 3 units of heat out of that unit. And you can see, so for example, of an ambient temperature of 10 degrees, so when it's 10 degrees outside, that same unit, if it was trying to generate heat at 65 degrees, it would be operating below 2.5, so something like 2.3. And if it was only having to produce heat at 55 degrees, it would be up near a 3. So this obviously has significant effects, impact on the cost of heat to residents as well. So, the lower the COP, the more expensive the heat being generated by that technology is. So just to move away quickly from heat pumps. So we can see the challenges with heat pumps. We need to get temperatures down. How we've approached getting networks to that stage where they can be, the heat numbers can be used with that heat network. We go through this process. So first of all, we measure the performance of the heat network, usually through data, if we can get data, or as with the HNOO project, through site audits, observations, interviews. Then once we've gathered that data, we analyze it and come up with the interventions, proposals, and the business case. So the HNOO project effectively took us through sections 1 and 2 of our typical improvement process cycle. The next stage would then be testing those intervention measures, those proposals, and then assessing the impact of those, and if they prove to be successful, then fully implementing and rolling out those improvements across the entire heat network. And here's just a quick example of the type of data that we'd be looking at. So this is from a single dwelling, and the dark blue line shows the network temperature, flow temperature, and the dark green line shows the primary return temperature. And effectively what it's showing here is this an example of an HIU that's performing poorly. So the very close between the flow and return temperature shows that the unit's not working particularly well, and there's an issue with that unit. So this would be a good example of where we want to go into that dwelling, look at how that HIU is performing. Is there something different to the way that's performing to other HIUs? And then through that gathering of knowledge, we can then propose interventions to roll out across the site. And again, something that's been brought up earlier in the HNOO presentation is that, luckily or unluckily, depending on how you want to look at it, unfortunately, historically, there's been a significant oversizing problem in the UK building industry. So pipework's oversized, pumps are oversized, plate heat exchangers are oversized, and there's oversized radiators within people's dwellings. Now, actually, this luckily now is providing us with a good opportunity that we can run, what we see a lot, that we can run the systems at much lower temperatures, and they can still work with the same pipework and radiators and pumps, which gives us an opportunity to drop temperatures without having to do very expensive intervention works. And here's a really quick example of the kind of thing we're talking about. So this is where we're dropping, the yellow line is the output from a radiator, the demand in a flat heating. And this was during a day where it was about -2, -3 outside. And you can see that the installed capacity, the blue dashed line, the design temperatures is about 6.5 kilowatts. And that dwelling actually was really only drawing about 3.5 to 4 kilowatts. And you could actually drop the whole temperature of the system down by 10 degrees and there'd still be comfortable headroom. So that's already shown that we've got an opportunity to drop the temperatures of the system without having to replace a lot of equipment within people's dwellings. And I'll quickly go through this slide, but again, similar to the HNOO project, these were the kind of issues we found. So, recommissioning, network bypasses, insulation, replacing plant equipment, and implementing better controls of the plant room. So quickly before I hand over to James to talk through the Wharf project, so this was a Notting Hill Genesis project, 86 dwellings, all underfloor heating and instantaneous hot water delivered by HIUs. So James, over to you.
Good afternoon all. Yeah, so the purpose of this is just to go through a case study and really just focusing on how actually practically these works proceed, and going forth from where we've identified the issues from the end of HNOO through to actually implementing on site. Yeah, so to start with, we start in the typical process. So we determine the key issues being experienced by bringing together all of the available data sources, and also bringing in the stakeholder information and then analysing the data. So we obtain information through discussion with residents, Naughton Hill Genesis themselves, the O&M contractor, and also conducting a rigorous site audit ourselves, which included detailed dwelling inspections, and then also having a review of all the available data on site, namely from the heat meters, but also from the BMS. And what came out of that really was that we had issues on the site which consisted of overheating of corridors. So it's commonly found that there were high ambient temperatures in corridors, which is a resident comfort issue. Also, the required heat tariff on site was causing a very high cost of heat. Also, the reliability of the HIU wasn't where it needed to be. So we're actually seeing a lot of valves failing on sites at the HIU, which is causing issues with heating and hot water supply. So that was a clear resident comfort issue there. And then moving on to the maintenance costs, this is actually related to the poor reliability of the HIU. There were a lot of call outs required on site and repairs, which again added to the residents' perception of the system being poor. Another point to note here is that there were very high heat losses from the pipework, which was actually impacting the cold water temperatures on site, which were seen to be above 25 degrees in some instances. I think it's the delay on the. I'm going to go to the next slide, please. So based on the audit findings, we developed a package of interventions, and really this was just focused on addressing those root causes of the identified issues. In the dwelling, that consisted of replacing the HIU to get over those issues identified with reliability on the existing HIU, but also we wanted to take this opportunity to retrofit a metering system that would allow us to remotely monitor the data. That would both help on the short term, so to verify the success of the works, but also long term on the maintenance of the system. We also identified areas where we could recommission the heating system and improve the residents' heating controls. Looking back at the plant room, so there are a few aspects that we identified as room for improvement. So the pumps were oversized, and if we were to replace these, we could actually bring those energy costs down. And there was a similar case with the plant room controls and the current hydraulic arrangement. And again, talking about heat losses, the heat loss from pipework was higher than what we'd expect to see. So really, there was a re-installation exercise there because we did identify areas of non-compliant installation. Sorry, moving on to the next slide. So the dwelling works, this shows the pre and post works HIU replacements. Now, the old HIU is not performing well. So with the new HIU, we selected a model that was more reliable, and we also engaged the HIU manufacturer to ensure we actually made this a bespoke solution. So as you can see on the right here, we had to procure a bespoke solution to ensure that the pipework installation was correctly orientated. And yeah, I mean, two key aspects of the success of these works in the dwelling were resident engagement and communication. It's really important to ensure that the residents are well aware of the works and actually buy into it. as well. But again, as Tom mentioned, a key part is conducting a pilot exercise to monitor how the first set of dwellings has been installed and implemented, and also to capture those lessons learned to implement on the rest of the sites for the full rollout. Yeah, and as I said, on the metering system, this actually allowed us to verify the success of the works and ensure that the HIUS are maintained appropriately. Moving on to the plant room, so one key aspect of the works was replacing the oversized pumps. Now, this is a great pre and post works photo. It is quite striking to see how oversized the pumps were originally. And as you can expect, we actually found that the pump electricity consumption on this site was very high. But I think another key point to note here is that even though we're replacing the pumps with smaller pumps, the smaller pumps are still more than enough to maintain the required performance and reliability of the heat network. And so looking at the impacts of the works, now on this graph here, we show the plant room flow temperature in blue, the return temperature in green on the top graph there, and the flow rate is shown in light blue on the bottom graph. Now, the system's currently operating at 70-degree flow temperature, and this graph shows the final HIU being replaced. Now, what can be seen here is we're actually getting 60-degree returns, but as we bring in that final HIU, the return temperature drops by 20 degrees. Now, at the same time, there's a significant drop in flow rate. And this is great to see because we bring down those heat losses from the network, but also we bring down the pump energy consumption, because actually, as you can see on the light blue line here, the pumps are actually reacting to demand. So they're actually reacting to the flow rate on the network as per the respective hot water and heating demands throughout the day, which wasn't happening before. So we have the flow temperature at 70 degrees, and really the discussion here is how do we get it down? So actually we could reduce the flow temperature here down to 65 degrees initially. So that shows that we've had a big impact on the system heat losses, and also help to prepare the system for future decarbonisation. So at the moment it's currently operating at 65, 40 or 45. And now the next step of this is just to look at how we can bring that down further. The key point is on this site that we actually don't need any more invasive works. It's simply a case of tweaking the performance of some HIUs and going forward with some commissioning adjustments on them. In terms of lessons learned from this, really, I can't stress the importance of high frequency data. If you can't measure it, you can't improve it. So if we have good access to data, we can quantify the issues and also improve the system in line with desired outcomes. I think that relates to heat networks in operation, but also if you were to do these sort of works, make sure the data analysis you have in place allows you to monitor the system. Yeah, so the dwelling often dictates the heat network performance, and typically it's overlooked. And again, I can't stress the importance of engaging with the residents early and often, because they really need to buy into these works and see the importance of them. And on this project, we worked with a company called HIUS. It was great to see that they engaged in the project and actually committed to the outcomes of it. I think that's key. We really need to make sure that contractors doing these sort of works are aware of the issues. I think at the moment that's not the case, but as we see more upskilling in the industry, that would be a crucial step to overcome. And in terms of outcomes, so we saw reduced heat losses, and also we have a great visibility on the ongoing performance of the network. We haven't heard of any reports of overheating in corridors. There's also a greater reliability of networks, so the provision of heating and hot water on site is more reliable, and this ultimately leads to a greater resident satisfaction on the heat network. Now, at this point, I'm going to bring in Laura, who is going to share some of her experiences on the project, but then also just some wider business related aspects relating to Naughton Genesis' path towards decarbonisation.
Great. Thank you, James, for that. That was really good for me to listen to as well. And just in terms of feedback, I'd say internally, Goats Wharf is perceived as a really successful scheme, both in terms of the implementation, because I think that FairHeat and suppliers made sure that it was designed around resident needs. And as a result, we got much better access rates than we usually do on other projects, but also in terms of outcomes. So everything I think James has just mentioned here, we've got a more reliable system, we've tackled issues around overheating, and obviously all the efficiency improvements have a positive impact on the tariff. So overall positive result for Naughton Genesis. I've been asked to share briefly in 5 minutes our experience in Naughton Genesis of improving network performance, which will also help us get carbon ready. I'm not sure if we can move to the next slide. Brilliant, thank you. Yeah. So it's worth saying in terms of Goat Wharf and other projects, I mean, that sort of demonstrates that actually beneath the surface there's some really positive things happening. And what we are trying to do now is really kind of take the learnings from these projects and understand whether there's a roadmap. I know I've heard this word used before, but a roadmap for a typical sort of housing association operated heat network to become more sustainable. Now scale is an opportunity, but it's also a challenge for us. So it's about how we take elements of the approach at Goats Wharf and apply it to 140 networks that we currently have in our portfolio. So FairHeat has said it would be useful for me to talk about the challenges, I suppose, both in terms of being a network operator, but also in terms of delivering network performance improvements. And it's worth saying that our challenges are our drivers and vice versa. And these challenges really for us sort of underpin our business case for network optimization. And these can really be themed around 3 things. So one is cost. At NHG, we've been on a bit of an eternal journey. So a couple of decades ago, we would have had a few hundred residents connected to heat networks, and that number now stands at 10,000. And these are kind of complex dynamic heat networks that traditionally we haven't had experience in operating. One thing that the board has woken up to during this time is cost, the cost of operating these networks, just because it's a bigger part of our business. But what is also focusing minds is the impact on costs when a scheme doesn't meet its performance expectations, or where performance dips, and the associated sort of repairs and maintenance challenges that come with that. Married with this then is a social challenge. So for us, really, in the past year, COVID has shone a light on the affordability of our heat tariffs. And I think for a lot of people, particularly for housing associations, they will say that our residents know there's a connection between how efficient a heat network is and the price of heat they pay. And there's a growing call for transparency around this that's just not going away. So this is about sort of the trust relationship and the basic social compact that we have with our customers. So for us, there's a cost challenge and there's a social challenge. And the third challenge is a regulatory challenge. We all know that decarbonisation is coming, but we don't yet understand the full impact of costs and what exactly we need to do to deliver this in a way that benefits our residents. What we don't want to do is get left behind our peers. So we're at a bit of a crossroads, stand still, and we know that the risks for our portfolio across all these 3 dimensions will be greater. Go forward, and there are benefits that we could potentially leverage. So what are we doing, and what are the continued challenges? So if I could have the next slide, thank you. So there are 4 things, and this is really sort of our mantra. We plan, we integrate, we develop partnerships, and we innovate. In terms of planning, So we have a heat network plan that spans 4 years and captures issues across a whole sort of life cycle, from design, commissioning, operation, and life cycle replacement. These are all processes that have to be designed with performance improvement in mind. We can't get this over, right overnight. We can't upskill our supply chain overnight. We can only do that with a plan. And it's likely that this plan will obviously project further into the future when we, start to think more about decarbonisation. The second point around planning is we need the investment that goes with it. But in order to build a financial business case, we need an information base. So, we know that not only can data help us identify some of the problems, but it's only really with, the data that we can identify the potential cost savings and benefits. So the challenge for us really in managing such a diverse portfolio is that we have multiple different types of meter technology and AMR systems. So, how do we unify our data pool? And that's particularly important, for managing performance improvement on more of a day-to-day basis. So the second thing is about integration, and I think this is a point that Joel picked up that is probably quite specific to housing associations, and that we work across different departments. So, typically there are different teams responsible for designing and operating heat networks. So we need to ensure that, KPIs and performance criteria, and this is one of the things that we're working towards, are built into our construction contracts and consultant contracts. And then these kind of seamlessly flow into our operation and maintenance contracts. We're looking at setting up commissioning processes with clear expectations for all parties and clear paper trails. Do we have the skills and expertise to do that? No, it's not going to happen overnight, but we have to start somewhere. In terms of integration, the second point is, aligning services. So building on, I think the first point, access isn't always an issue and it's a cost. So we're looking at trying to deliver improvements alongside our HIUS servicing program, and then using data to, observe before and after results. And it's also a really good way of ensuring that, the work we've specified has been carried out appropriately. So this isn't just kind of like a one-off way of working. It's something that we're kind of, we're quite keen to embed. Partnerships, I've put partnerships here because it's a really big part of our plan. We're not going to do this alone. There's lots of really interesting things happening, lots of forums being set up where people in, on a similar journey can share expertise. It's not just about sharing expertise. I think that we need to standardize approaches. So the industry is kind of pulling together in one direction. And, one of the things around that is standardizing how we measure performance. Innovation. So I think we all know decarbonisation, we're talking about a step change. This is something we're not going to achieve by, just integrating and just planning. We need to collaborate with our supply chain, with entrepreneurs and businesses, not just in terms of technological solutions, but also in terms of, the business plans that are going to, business models, that are going to allow us to invest in decarbonisation. This is a huge, huge challenge for us, and one that we need to understand better. So there you are. That's the beginning of a sort of roadmap for Nottingham Genesis. It's not perfect. The challenge for us is that we need to deliver this at scale, but I think there's some positive things happening that provide us with a good foundation.
Excellent, thank you, Laura. That's really fascinating seeing it from perspective of a housing association. Sometimes we focus on the technical side of it, but there's actually a lot to do with decarbonising and optimising heat networks is really people and organisational change. So that's really interesting. Thank you. Okay, on to the appreciate we're running slightly over time, but on to the next. So we've looked at existing heat networks through like how to optimize them and how to get them to a state where they can be integrated with heat pumps. We're now moving on to looking forwards. So how do we integrate heat pumps into new build heat networks? So what the next generation of heat networks going to look like? In this presentation, we have Mike Ridge, so principal engineer at FairHeat. Can you skip to the next slide?
Yeah, I'm trying. It just Not letting me at the moment.
Okay.
Okay.
Perfect. Okay.
Yep.
So you've seen Mike Ridge now, anyway, on the video. So Mike Ridge is principal engineer at FairHeat. He heads up the new build side of FairHeat and looking at, how do we get to this? Chris Davidson is, I was going to say A, but I'll up a bit more to the ground source heat pump specialist. And he's here for a second time as well. So he came to our last anniversary. So he's a welcome guest back. And then we also have Paul Carty from Ballymore. So maybe a bit of perspective from the developer's role of how to integrate heat pumps into heat networks moving forwards. Okay, so over to you, Mike.
Thanks, Tom. So yeah, last year I presented at our birthday event and I was talking about energy strategy in general, and it was very much planning for heat pumps, and heat pumps were coming because of policy changes, the new London plan and decarbonisation. And 12 months on, as I was putting this together, I was looking at how many projects we'd worked on in the new build sector energy strategy stage, and it was over 15 since that last talk. And the common theme on all of them was integrating heat pumps into heat networks. So it really doesn't feel like heat pumps are coming, it feels like heat pumps have arrived. I think that's really exciting from a both decarbonisation perspective, but also particularly in London and dense urban areas, a local air quality perspective. So I'm just going to share some thoughts on some of the challenges we've come across in supporting clients with the technical challenges of integrating heat pumps into new build heat networks. In terms of new build, in terms of decarbonising heat in the UK in general, I think we're going to see heat pumps in two guises. In low density, we're going to see individual heat pump systems, but in medium to high density, I think that heat networks, so fourth generation, fifth generation, low temperature heat networks are really going to be one of the key technology infrastructures to get heat pumps decarbonising heat. So I'm just going to talk through some of those challenges, but in terms of why heat networks for those medium and high density developments is technology agnostic, which means it can be served by a multitude of different technologies and they can actually be changed over time. So it's a vehicle where we can decarbonize over time and we can transition into lower and lower carbon technologies over time. As we kind of heat networks become more established in the UK, particularly in London and some of the other cities in the UK that have embedded them in their strategies, we'll eventually have some system interconnectivity. That means we can play around with energy sources and optimize running cost decarbonisation at any given time. We know it works. We know it's proven to decarbonise. I mean, Gareth in the morning mentioned about the Scandinavian models and how they've used heat networks to decarbonise heat. And in the UK, we're actually a long way down that experience curve. We're talking about how to improve some poor performing schemes that have been operational for a while, but we have also come a long way in the new build area of the more recent heat networks, are getting some really high performing heat networks coming through. So some of the technical challenges that I've come across and the new build team has been trying to help clients solve over the past 12 months, and I'm going to talk about now. It all starts from a heat pump perspective, both in new build and existing heat networks, in minimizing the generation and distribution temperatures as far as possible to boost heat pump efficiencies. Maximizing thermal storage is a common theme through all heat network projects. But it has challenges in terms of where to locate that thermal storage and how to design it. Technology selection, not just jumping to a default air source, actually challenging at an early possible stage to consider others, and also the impact that different technologies have on site-specific constraints. And then plant location strategy has been a really common theme for me. That is often one that gets revisited later in a project's journey because actually decisions were made that weren't necessarily the impacts of those weren't fully understood at the time, and then we have to kind of start from scratch a little bit again. So in terms of minimizing distribution temperatures, we've heard a little bit about this already, but it's that thought process of, I'm not just going to jump straight to my energy center design. I'm going to start a new build development by thinking about what temperatures do I need to get to the end dwelling. So in the tertiary system, space heating, domestic hot water, What temperatures do I need to distribute at? Do I need substations? Are they actually necessary? Can I remove them? Because every time I have one, I have to have those jump up in temperatures, so that I then get back to what generation temperature does my energy center need to produce, and is that suitable for the heat pump technology I've got in mind? Tom put this up earlier, so I'm not going to go over it too much, but as well as heat losses, this distribution temperature is all about, particularly for air source, improving the efficiency of the overall system by not asking it to operate at an extremely high temperature. And this again is the Mitsubishi Chav, but just taking like an annual average temperature that we would typically see at 10 degrees. The difference between operating the system at 55 as opposed to 65 is a 36% increase in efficiency at that ambient temperature. So there's massive gains to be had by getting the distribution system temperatures as low as possible. And that really starts at stage 1, stage 2 design. So in new build, the goal is 60 degrees, the maximum we really want to be distributing at for heat pump systems. And when we've got twin plate HIUs delivering instantaneous hot water and space heating, we really want that a 10-degree forward approach from what we're delivering to our HIU from our heat network to what we're delivering on the dwelling side, particularly with the space heating systems, which puts a threshold for 60 of 50 degrees on our dwelling systems. And that has quite big implications for space heating systems. That's one of the most common issues we come up against when we're trying to integrate heat pumps on new build developments. Because 50 degrees is quite low temperature compared to conventional tertiary dwelling heating systems. So this diagram is showing 60 degrees coming in from our heat network to the HIU and supplying 50 degrees to our space heating system. Now for underfloor heating, that's not a problem. Most commonly, we would see underfloor heating systems designed at 45 flow temperature, so that can easily be delivered from 60-degree flow temperature on the network. But for radiators, and a lot of developers have done radiators for a long time, that's what they're comfortable with. 50 degrees is a lot lower distribution temperature than typical. You know, we've moved from 80 degrees down to 70 degrees, and in some cases we've started to move to 60, but 50 degrees is a step even further. And these radiators start to become quite large. So while technically feasible, they do add cost, and they really need to be considered very early on in the architectural process. The alternative is to go for a direct system, which is a real challenge on tall systems because the pressures become untenable to enter people's dwellings. But it is an option where you remove the plate heat exchanger from the HIU and just have it for the hot water, and the space heating goes direct through to the heat network, which means we don't need that step down in temperature, and we can pass that 60 degrees straight through and get 60-degree flow temperature to the rads, and they start to become a little bit smaller than the 50. Just to put this into context in terms of, well, how much bigger do these radiators become? If we look at this graph, which shows the increase in radiator size that results from moving from a 70-40 counterfactual of maybe 3 or 4 years ago up to supplying radiators with a 50-degree flow temperature, they're doubling in size. And even actually going from more recent radiators such as 60-40 up to down to 50 degrees, they're about 1.5 times the size, if not more. And so these start to become either very wide or very deep, which gives its own kind of design challenges. And obviously the cost goes up. And also spatial constraints around, you know, how much they eat into the space of the living room, how much wall space do I have? Do I need multiple radiators where I would have previously got away with one? These are all things that need to be considered very, 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 very early on to make sure that the 60-degree flow temperature is actually feasible. So the next thing I'm talking about is maximizing thermal storage. The reason thermal storage is so important for optimizing heat pump design is because of the nature of residential heating and hot water demand being extremely peaky. So we have really short duration but large demands that represent the peak demand when we have a coincidental coldest day outside in the morning when people want hot water. We have a surge in demand, but for most of the year the demand is actually, it's like a base load. It's very, very low level demand, which kind of divorces what we want the heat pump to be doing for our base load generation from our peak demand situation. And what this graph is showing is showing the amount of time spent at different demand during the year. So for 90% of the year, we actually typically see heat networks sitting below 50, actually below 45% of the peak demand. So this is for a typical 500 dwelling scheme where the peak demand is around 1.2 megawatts, 1200 kilowatts. And actually for 90% of the year, 90% of the heat demand is occurring below 500 kilowatts in this example. Moving that further down the curve, 80% of that heat demand is occurring below 35 per peak, and 50% is occurring below 20% of peak. And when we start to think about the role of heat pumps, quite an expensive technology in comparison to gas boilers in terms of the pound per kilowatts, what we were asking them to do, this becomes quite a powerful design tool in terms of how we think about sizing our systems. So, for example, using the same 500 dwelling scheme example, we can actually provide 20 to 25% of the peak demand through heat pumps by sizing them, say, 225 kilowatts. But in combination with thermal store around 20 meters cubed, we can meet 80% of the annual heat demand. Then to provide that additional 20%, we have the boilers doing some peak loading. It can either be gas boiler, it could also be electric boiler, depending on the constraints on the site and whether gas is in the mix or not. This becomes quite powerful when you compare this against trying to do peak demand solely through heat pumps. 1200 megawatts, 1200 kilowatts of heat pump. One, needs a lot of space, and two, it's extremely expensive. So these are the kind of considerations, and using thermal store to play around with the difference between peak demand that's coming from the site and when the heat pump can operate to really reduce that total heat pump capacity while still meeting the end user demands. I think it also becomes really interesting when you push this boundary to say, well, what if I want to deliver 95% of heat from my heat pump and thermal store system? And actually, it doesn't become, increasing that heat pump capacity all the way up that peak demand curve so that, you're installing a megawatt of heat pumps. You can push it up just to 30, 35% of peak demand, increase the thermal store that bit more. And for a scheme such as this, you can have a heat pump capacity of 350 kilowatts, so about 35% of peak demand, some large thermal stores, and that circuit on its own could do 95% of that annual heat demand. And then you're only asking your boiler to do 5% of the annual heat demand. Now, it might be quite a big boiler because of the nature of that peak demand, but it's a very cost-effective way of decarbonising a large portion, the vast majority of your heat, but a very capital cost-effective way, and also maintaining an acceptable cost of heat to residents. In terms of the hydraulic design of thermal storage, I just wanted to flag, the BEIS compliance, particularly in the London plan that's coming through. Promises that are made at energy strategy stage are going to have to be delivered against, and we will have to report operational performance data and prove that we're delivering against those energy strategy compliance. And for this, we need hourly load models to make sure that the design tools we're using are accurate, and we're getting really good accurate load estimations to size our heat pumps, our thermal storage to meet those promises. And the designs have got to be really well thought out in terms of their hydraulic arrangement of heat pump, thermal store, boilers, buffer, control valves, control logic, and the overall controls philosophy that really gives us that guarantee that we will utilize those heat pumps as much as possible and get that 50, 60, 80, 95%, whatever the energy strategy promises, that's going to be achieved by the design. So if we look at what's happened historically with the CHPs, that simply hasn't happened. But that won't be the case in terms of compliance anymore. So utilizing that thermal storage is absolutely key to getting the most out of your heat pumps and not oversizing your heat pumps as well. In terms of technology selection, my experience and in general is that air source heat pump is the de facto starting point, and particularly when you get into the challenges, site-specific challenges that can impart on a site around, rooftop space. Where are we going to locate those heat pumps? Do we have enough space? I've got a very, very tall development, so I can't locate the whole plant room on the roof. So I've got to go from the air source to ground and then back up again, and it starts to become maybe quite inefficient. alternative technologies such as ground source or water source in those examples can be quite attractive, and they can be very technical feasible options. And particularly with RHI on ground source, then that can alleviate the capex constraint that is associated with ground source. And that's what Chris is going to talk about later, and why we've had a really good partnership with Chris and Genius Energy Lab, is that looking properly at ground source at stage 1, stage 2, and doing a proper site-specific technical feasibility study will answer those questions rather than a little bit of a discounting ground source too early on. So the differences we're looking at is, in general, air source is going to be lower cost solution than ground source. However, we're going to need more rooftop space or more plant room space to make that possible, which in some developments is just simply not an option. Ground source is going to have much higher impact on your construction program than air source, and open loop is going to have probably significantly more program impact than closed loop due to the permitting and environmental agency permitting requirements that are associated with that. From a generation cost perspective, I think ground source is likely to lead the way because of its lower dependency on ambient conditions. Air source at the moment, you know, that sensitivity with its poor performance when it's at -3, -5 degrees outside is going to push the running cost of air source heat pumps compared to ground source heat pumps up. But I think the use of thermal storage and innovative control systems that decouple site demand from generation timing should bring that down, and something we need the industry to bring through. Maintenance and replacement, we've done quite a bit of work at looking at this, and closed loop, I mean, Chris will talk about this later on, but that's your kind of lowest, I mean, I don't like to use the term fit and forget, but in terms of, you know, maintenance, that's the lowest cost option. Open loops are a bit more complicated and requires more annual maintenance. And then similarly with air source, you know, you're maintaining rooftop plant, getting access to that plant has costs associated with it. RHI, I'm not an RHI expert, it's changing all the time, but obviously that's where ground source can come into its own, and you can still get really good tariffs and kind of offset that capital cost associated with ground source. And I think that needs to be utilized a lot more than it is, and considered a lot more at energy strategy stage in terms of whether that can make the difference between ground source being viable or just discounted too early on capital cost grounds. And the key, what I'm trying to pick out of this, and in part on particularly developers, private developers, housing associations, local authorities, is don't take things off the table too early. That, you know, technologies offer different technical feasible solutions, and there's likely to be multiple different options, and link it to your site specifically in terms of the constraints that you have. Don't be led by going down air source or going down a particular manufacturer. Take a step back and look at what your site constraints are, what your risks are, and what fits best into that. I wanted to put water source in here because I haven't done a lot of work with water source, but I do feel that it will eventually need to start playing more of a role in the UK, because it can't just all be about air source, and we've got to make use of our resources. It's going to be comparable to ground source in terms of that cost profile, but it is quite obviously very project specific, and it's quite specialist, but it can, you know, really offer some high efficiencies, and it will be an essential part of the long-term solution. And there's some really good examples out there that I would encourage people to go and take a look at, such as the Queen's Quay example in Glasgow with over 5 megawatt of water source heat pumps. That's a really good scheme from a decarbonisation perspective. So the last one, to be honest, probably the one that I've spent the most time kind of being involved with is plant location, and one that often gets rolled back a little bit in terms of back to the drawing board. So for air source heat pumps, one of the options is to have a split strategy where the air source heat pumps are located on the roof, and we have thermal storage distribution, maybe some boilers at ground level, and then we distribute out from there. And where rooftop is relatively restricted, but there is some available for air source, that's probably likely to be the optimal strategy. However, something I wanted just to highlight that is often discounted again too early, but is then brought back on the table when kind of further constraints start to make the original energy strategy not really viable, is entirely rooftop package plant rooms, even for hybrid systems involving gas or electric boilers. Look at the space your solution needs. Try to understand whether actually it is a better solution for that all to go on the roof. You know, you're removing a flue going through the building, potentially you've got to take the gas up there, yes, but you know, there's pros and cons there. And sometimes this can be overlooked, but it's definitely worth considering at stage 1, stage 2. And with ground source, you're going to likely have a single ground level plant room, trying to find the optimal location for that, and then distributing site-wide from there without any need for a rooftop plant. So from my perspective, trying to wrap up quite quickly to catch up some time, it's all about starting with the dwelling and building, because temperatures are going to dictate how efficient and how cost effective your system is to run. Thermal storage is key. It provides you operational flexibility. It can reduce your required heat pump capacity. So don't just ask what's the minimal thermal storage I can get away with, or that I can kind of fit in my plant room without really challenging it. It's what benefit would additional thermal storage provide my system and provide my residents? And then challenge, you know, your spatial constraints. Can you dig a pit in the energy center to make the thermal stores longer, but without increasing your spatial footprint? Really challenge that design to make sure you're getting the most out of thermal storage. And then make sure the hydraulic designs are being backed up with, you know, we're going to prove this energy strategy, and we've got confidence that when we meet to this, it's going to meet our promises. Challenge the technology selection, make sure it's in line with your preferences from a developer's perspective, and from a consultant's perspective, you know, make sure that everything is being considered on the table and that it's being considered within site-specific constraints. And optioneer plant room locations at stage 1, and common theme, particularly on this one, do not take options off the table too quickly, because sometimes actually thinking again can put a little bit of a different light on the situation and give you a more optimal solution. So I'm going to hand over to Chris. Chris, do you want me to drive, or do you want me to hand over?
Please, Michael, yeah, if you wouldn't mind.
I'll drive through, yeah.
So if we can just stay on the first slide for a start then, Mike. Just so, good afternoon, and thank you to FairHeat for hosting what I have to say has been a fascinating day. I've been engaged the whole way through. I've learned a lot, and I've really enjoyed it. So thank you very much. And thank you also to Tom for your very kind introduction and promotion at the start of this session. So our relationship with FairHeat goes back over a year now. Genius Energy Lab, we're a high performance small consultancy providing ground source heat pumps, specifically advice from design through feasibility study. And we actually did a couple of days training for FairHeat just over a year ago. And it was great to see the attendance from the FairHeat team. It was really a well-attended session, and some fantastic interaction with the FairHeat team. And I think what became clear to the team during those 2 days was that there was a need, when we talk about ground source, to get involved with some specialist advice, or to maintain that involvement with specialist advice. And so as a result, we've done a couple of studies during the course of this year, which we're going to talk through on an anonymised basis, because they're actually real projects that there are NDAs in place on, and so on. And I think the need for that specialist advice in large part comes from the broad range of skills required to assess ground source heat pumps properly. Everything from a good understanding of building physics, building services engineering, controls, hydraulics, to geology is required to really assess ground source properly. And the great news is, there are quite a number of specialists around the country who will give you that excellent advice. And also, I think at a price point that's very useful to get in early days, as Mike was saying, get that information in early days and be project specific. And I think the reason it's very important, particularly at the moment, is that mainstream building services engineering just doesn't have that skills at the moment. It resides in smaller businesses like my own. And there was a very interesting study done by a contemporary of mine in North America a few years ago, by which they ascertained that something like 80% of viable ground source projects are written off at early days for sometimes very spurious reasons, perhaps using rules of thumb to work out how much pipe would need to go in the ground, perhaps using rules of thumb on costs that were inappropriate. And it does break my heart, I have to say, to see in energy reports, early days energy reports, some of the really spurious reasons that are used to discount ground source. And sometimes you have to feel that they just don't want to get involved in it. But I think with a bit of specialist help, it would be a lot easier than perhaps people think. So on to Project A. This is a two-phase project and 200 dwellings and 750 dwellings. Going back to what Mike was saying, we looked at a good range of load requirements to try and tailor the best option to that project. And that's common when we're looking at ground source projects particularly, is to think about the different options, as Mike said, to fit that load profile and get the best cost profile for that project, from install costs through to run costs at the end. And what we're really looking at is local conditions. So we've got a thorough geological analysis first. In this project, it's in central London, and the majority of the map, certainly the top of the geological map you can see there, is that sort of pinky brown colour is the London clay. London clay is the common surface geology in quite a substantial amount of London. And I think when lay people come to geology first, they'll often make the mistake of thinking that that's London clay all the way down until you meet Jules Verne coming up the other way. Well, actually, the geology is in layers. It's called the Thames sequence, and it goes through the London clay into some sands and gravels and then into chalk. So that gives us lots of options. We could drill closed loop, stay in the London clay, which is a relatively poor conductor, but an excellent drilling condition, or we could get through those more difficult sand and gravels and do deeper closed loop into the chalk. So closed loop is just drilling narrow diameter boreholes and putting a single U-tube of pipe in each one. But we also have open loop opportunities in much of London, with the top layer of the chalk, particularly the top 20 metres of the chalk, having water in it. So there are both closed loop and open loop opportunities, open loop being where we're actually putting water wells in to take water from the ground, warm it up or cool it down and put it back into the ground as well. And that brings me on to another very quick point. Cooling is incredibly important in ground source. If you've got any cooling locally, could be just some shops to serve the development or so on, anything like that is worth grabbing hold of with both arms and keeping control of it. Thanks, Mike, you're telepathic. It was fantastic. And I think I'll just touch base on one item, is that the closed loop in particular, which came out best on this project, is a long-term asset that's going to be there for 50 or 100 years and can be operated much like the gas, the electricity and the water infrastructure has been over the past many years. The title's missing off the top one, that's maintenance cost. You can see the three options there with the maintenance cost for the system. We assess the run cost savings, and I'll just touch on run cost savings. They are heavily influenced at the moment by the spark gap in the UK, so the difference between gas and electricity price. A rebalancing of that, because quite frankly, the gas price at the moment is subsidised and the electricity price is levied. And the justification for those levies is that electricity was historically a high carbon fuel. It's low carbon now and getting lower every day. And so the rebalancing is really on the cards between the gas and electricity price. So that will really affect those run costs ongoing. And then we did the IRR calculations you can see there. So it's typical of what we're providing for FairHeat. Project B, slightly different spin on this. Geologically, again, very similar. So it's a London project again, but that specific analysis is very important because the relative thickness of those layers varies across London, and with their conductivity and their opportunities for open and loop changing as well. So just to talk about this in a little bit of detail, the importance of building loads. Oversizing has been talked about today. Oversizing from a ground source point of view is catastrophic from a cost point of view, but also we need to understand the annual loads. So we start to break these loads down by month in order to give us adequate ground loop design information. And so that's very important, I think, for us. And it came out in this one, 56 bores at 240 meters were required to provide those loads in that table. I think it's really good working with FairHeat. Some of the best information, quality information we get is from FairHeat, as Mike mentioned earlier on. And then just talk very briefly on that before we get on to the next slide, is that the ground loop is a finite resource. And so we can run out of steam in that ground loop. It's not like buying more gas or buying more electricity. We can actually depress that temperature to the point where the system starts to struggle. So the importance of those loads is really important when we're talking about particularly closed loop modeling. And also phasing is important. In a 4-phase project, we really need to consider all the phases when we're looking at what that loop infrastructure needs to be when we're actually dealing with phase 1. And then again, a theme from the morning session, the importance of heating and cooling. Because this project was looking at both closed and open loop, we took on some feedback from the customer and looked at the pros and cons of the two technologies. If you want to see some more information on the pros and cons of open and closed loop, there's an excellent session of webinars hosted by the Ground Source Heat Pump Association, which goes into this in a bit of detail. So conscious of time, can I have the next slide? So again, we looked at the differential cost between the closed loop and the open loop options. And this became a study not so much of different size options, but different technologies that interfacing with the ground. And then final slide, please, Mike. Yeah, so finally, incentives. Just a very brief word on what Mike touched on earlier on. The RHI is tailing out now, and you can see some of the returns from the RHI were significant. But we are looking at a time of flux in the policy environment. The market is doing very well, regardless of that, with much more drivers coming into it. Rooftop equipment, for example, as Mike mentioned earlier on. I'll leave it with that, and I very much look forward to participating in the panel discussion.
Okay, yes, I've invited Paul Carty, Director of Construction at Ballamore, that we've worked as a case study that we've worked on, where it's a project that wanted to transition from CHP to air source heat pump strategy, and Paul's just going to talk about from a private developer's perspective, his perspective of the challenges and the benefits that process has had.
Hello, everybody. Can you hear me?
Yep.
The video won't start there, but that doesn't matter. You have a very dodgy photograph of me up already. So, okay. Listen, we engaged FairHeat, well, must be 18 months ago now, Michael, on a project in Dublin, Ireland. It's a, if you want to, can you slide the slides forward? Yeah, so what we have is a development in Ireland here. It's 435 apartments, a primary care centre, and about 4,500 square metres of other uses within the development. As you can see from the images there, it's an estate with 5 building blocks. So when we approached this project, it's a 200 million plus sale. It's an institutional sale, and the people who would be purchasing this development, who are in the process of purchasing, have a very strong due diligence team. So when we approached the project, obviously the heating was a very important concern for us. In Ireland, in recent terms, air source heat pumps, ground heat pumps were not used to the degree that they were in the UK. So we're a bit behind in that. So we wanted to try and accelerate our developments into this space. And some of this we fed off of the experience with FairHeat in London. And in Ireland, we have a Sustainable Energy Ireland, and what they had done on their deep calculation for the apartments, we have a BER strategy in Ireland, and we wished our apartments to be an A2 rating. And in order to do that, under the original deep calculation, the renewable aspect was always CHP or PV. And I've had very mixed benefits with both of those over the years. So what we talked to FairHeat. They were very good to us. They came in, they sat down, we did a peak load sizing review of the project. We looked at plant sizing and hourly reviews. We brought it onto a network and to network routing options. So we explored plant rooms in various different areas. We explored various solutions for pumps, and we looked at CHP and PV.
Go on to the next slide, please.
Yeah, please do keep going. Yeah. So for the heat pumps, we looked at lower levels of the development, and I suppose what we did was we put the Mitsubishis up on the top of one of the taller buildings at 13 stories. And the reason we did that was several. One, we had slight concern about noise. They're running at 59 dB, which is noisy enough. There were other factors about getting sufficient air around them, and then things such as ice and just the visual aesthetic of them. So we put them up on a roof. We found that we could get eight CAHV units on the roof, and it took up a space of less than 100 square meters, which was important to us, because one of the downsides on the PV, the equivalent PV, was coming out nearly 900 square meters. And on this development, the roof space was important to us, because part of the amenity in the external space was the various terraces. So we didn't want to use PV. So in order to accommodate this thermal storage, we redesigned the ground floor level. And as part of the air source heat pump, the 8 heat pumps, we matched that with 8 250 kilowatt Hamworthy boilers. And in fairness, Michael's previous presentation fed into Ormond completely. We ended up with 27 cubes of hot water, and we chose to come to the lower 60 degree generation staging. But what was very important on that, and isn't on that slide there, is we also we also chose various different networks around the estate, and we managed to save about 20% of our gun barrel engineered pipe work, which was an expensive solution following traditional routes. In fairness, FairHeat guided us into a different. We've come up vertically up the various risers. Excuse me, don't know what's after happening there, but so the thermal storage was 27 cubes, but it actually wasn't that difficult to allocate in our plant room. Now, the reduced radiator temperatures did increase our radiators by 26% on Ormond, and that wasn't too bad. We put 2 radiators in the living space and 1 radiator in each of our bedrooms. Our apartments are quite sized. They're 80 square meters for the 2 beds and 50 for the 1 beds. We have a nice high 2.75 ceiling, so there's good volume in the apartments. So FairHeat worked with us with Sustainable Energy Ireland, and we made a presentation to Sustainable Energy Ireland, and they allowed us to change the calculation. And so the standard base of the calculation, they accepted thermal storage, and they've now changed. So Ormond is one of the first projects in Ireland to have no CHP, no PV, and thermal storage with air source heat pumps as the basis of the calculation, and they were very impressed with it. So I think you'll see more of that in Ireland.
Next slide, please.
Please do, yeah. So look, in terms of the air source heat pumps, there is actually no disruption to the original architecture. We were able to put the air source heat pumps up on the roof. The gas boilers, we changed our plant room. We had a energy center, and then we had a cold plant room. 350 square meters for both has served the entire estate, so that has worked out very well. We have put this into our BIM solution, and so we're up at level 2 on the integration and federation of that model. The generation equipment, we located all in one of the buildings, which is block D, and that was the first building to be handed over. So it was very important to us that the entire energy center was complete within 2 years with the first handover, because the development will be 5 different handovers. We have significantly reduced carbon emissions, so it's much cleaner air. We are looking to use the air source heat pumps as the primary, 60, 70, 80%. We're going to have to look at trying to measure that. And in future, we've future decarbonised with which, please God, we will replace the boilers in the future. Now, the Irish energy consideration of gas and how gas is being used, gas has got a cleaner code recently in Ireland, but it was a very good experience for us, and I have to say thank you to Michael and the guys, and that we built a very good relationship with SEAI, and I think they'll be looking at Ormond as a test case, as we will be as we're constructing it. Is there another slide, Michael? Yeah, so that was good.
Paul.
Thank you very much. Okay.
I think we're going to get to the panel now, Tom. A little bit, well, significantly over.
I tried to be quick.
I know, Paul, it wasn't you. It was.
Well, one good thing about it was with COVID, poor old Michael and the guys couldn't come to Ireland, so we have more Guinness.
Excellent. Thank you all. Yeah.